In chapter 18. We just got done with the test in chapter 17, talking about the different types of energy and how energy can transfer from one form to another, and then how we use that energy to get the electrical needs and the mechanical needs that we need. Today we're moving on talking about thermal energy, specifically here in lesson 1, as we get moving in with this next chapter. And today we're going to talk about how thermal energy is transferred. You remember from last one, thermal energy is heat caused by friction sometimes, warming your body and things like that. So we're going to talk about what thermal energy is and then the different ways that it is transferred today. You got some note sheet that you're trying to fill out. I'll emphasize some of them as I go along, but it's kind of fill in the blank. You'll see this as we move along to be able to fill those things in. The summary statement for today says thermal energy is the total kinetic and potential energy of the particles in a substance. We had that on our test yesterday, even though they don't give us the definition until this chapter. Heat is thermal energy that moves from one substance to another. Heat can move by 3 types: conduction, convection, and radiation. We'll talk about that as we cruise through the lesson. Let's get introduced to thermal energy. When you look at the molten glass, it is easy to see that the particles are moving. So they're talking about this making glass right here. These things are moving because we're pouring it. The molten glass flows, but a solid object like a glass pitcher seems to be perfectly still. Are you surprised to find out that it's not? We already talked about this with the states of matter, how the particles inside it vibrate. All matter is made of particles that are always moving. So you can see what you're doing here as you fill in this blank with your notes. The particles have kinetic energy because they are moving due to motion. The particles in a substance always pull on each other. This means that the particles have potential energy, or energy due to their positions. Put those two together and you would call that mechanical energy, right? But the total of the substances of the particles is what we call thermal energy. Particles in a gas can move freely. They do not pull strongly on each other. Particles in a liquid can only flow around each other. They pull more strongly than a gas would do. Particles in a solid pull strongly on each other. They vibrate, but they cannot move from that fixed position. So they're moving, guys. And then if we had asked you which ones pull the strongest, solids pull the strongest. So weakest with the gas, then to liquid, then to solid. The total kinetic and potential energy of a particle in a substance is known as its thermal energy. The amount of thermal energy depends on the amount of a substance. So if you have a cup of water and pour half of it out, the part that is left has half the number of particles. Therefore, it has half the thermal energy of a full cup of water. So the more of the substance you have, the more thermal energy it has. Now, the reason they're making a big deal out of that, guys, is because that's going to be the opposite of heat. Heat is like temperature kind of thing. And so when I think about temperature, it doesn't matter if I have a full glass at 90 degrees or a half glass at 90 degrees, it's 90 degrees. But thermal energy says, hey, the amount matters, the total. And so if I cut that in half, we cut the total amount down in half. Thermal energy determines how warm a substance feels. A warm cup of water has more thermal energy than a cool cup of water. The warm and cool water have the same number of particles, but the particles in warm move faster. So they would have more kinetic energy, which would therefore give them more thermal energy, which we would say feels warmer because we're after total kinetic. So the more it's moving, the higher it is. Awesome. So you have cruised right down here. You got all the way through number 10 with your blanks filled in. Turning the page in your science book would look like this. Now we're going to start talking about heat. You've probably measured your kinetic energy many times, but you may not have known it. Temperature is, let me scroll your notes so you can keep cruising along with me. Temperature is a measure of the average kinetic energy of an object's particle. When you take your temperature with a thermometer, your body heat increases the kinetic energy of the particles of a liquid in the thermometer. The thermometer then shows the average kinetic energy of the particles in your body. So they talked about a liquid thermometer. That would be this guy. Today, obviously, we have digital thermometers, which is simply measuring the average kinetic energy. Okay, so obviously particles move at different speeds. It's like trying to look at a highway and I have cars going by. And I would say, well, the average car going down the highway is driving 65 miles per hour. Some are only going 60, some are probably going 70, but on average, it's 65. That's what heat is. It's just the average of all those particles moving. Temperature is not the same as thermal energy. Temperature depends only on the average kinetic energy. Thermal energy depends on the sum of putting them all together. Unlike thermal, temperature does not depend on the amount. If you split an object in half, each part has half as many particles, but the temperature didn't change. The average kinetic energy is the same. So that's going back to the last page and telling you how the difference is. Thermal, more you have, more thermal energy. Temperature, doesn't matter. Cut in half, cut in half, cut in half. It's still the same temperature, no matter how much of that substance you have. Thermal energy can move from one substance to another. That's called heat. Heat is the transfer of this energy. Heat always moves from a warmer substance to a cooler substance. An increase in temperature means that heat moves into a substance. When heat moves into a substance, the average kinetic energy of the particles rises. The extra kinetic energy increases the particle's vibration. Particles vibrate faster and faster when a substance is heated. The movement of heat from one substance to another can occur between objects that touch and objects that don't touch. There are three ways we transfer heat. It is conduction, that touches, convection, doesn't have to, and radiation doesn't touch. Okay, so we're cruising along here. You got all the way through number 17. We're going to start talking about this. This will be a challenge for us, guys. Heat always moves from a warm substance to a cooler one. That's how we are transferring heat. And so we're going to talk about the next page because we'll try to get that straight in our head to understand that. So here are the three types we're going to talk about. Today I'm going to take conduction, and then on next week, Monday, we'll get convection, radiation, how we increase transfer, and how we slow it down. Heat transfers between two objects that touch is called conduction. So make sure you understand the big thing with conductions, they have to be touching. Think about what happens if you place ice cubes in a glass of warm lemonade. Do the ice cubes cool the lemonade, or does the lemonade warm the ice cubes? If you ask me, what do ice cubes do? They cool the lemonade. But I got to go back over here and say, is that true? Which way does heat always go? Heat always goes from a warmer substance, the lemonade, into the cooler one, the ice cubes. So they're going to explain that to us. But what happens? The lemonade warms the ice cube. I'm going from something that's warmer into something that's colder. I am not taking something that's colder and pushing it into something that's warmer. So guys, you just got to understand science class. It's not like it's wrong to say ice cubes make a substance cold. It does that. How? It is absorbing heat. The temperature of the ice cubes is lower than the temperature of the lemonade. The particles that make up the lemonade are vibrating faster than the particles in the ice. When the ice touches the lemonade, the particles in the lemonade bump into the ice particles. This causes the ice particles to move faster and faster. The heat is flowing from warmer lemonade to cooler ice. The lemonade particles slow down and cool down. Conduction of heat has warmed the ice and it has cooled the lemonade. When heat moves by conduction, the particles in the substances do not change their location. Energy is passed from particle to particle as they vibrate and bump against them. This movement of energy may occur between warmer substance and a cooler one. It may also occur between a warm part of an object and a cool part of the same object. Okay, so I decided to burn myself by putting a fork on the burner. The fork is touching the burner of my stove, and it's going to transfer up the fork until it gets to the end of the fork where my hand is, and then that'll get to my worm. So that's all they're saying there is. In example 1, I had two different substances, lemonade and the ice cubes. Down here, they're saying it doesn't have to be two separate substances, just so you know it can be the same substance. So a piece of metal will conduct heat through that piece of metal, and it'll slowly speed up the particles as it works its way through that. Okay, they gave you here at the end here just a few different temperatures that are out there between the surface of the sun, what we talked about, sometimes those light bulbs, how hot that can get inside it, and the danger that is it. We've obviously improved that with time today. Your oven that has a glass flame, or your furnace, we can melt iron, and it's kind of crazy to think like lots of times the blue flames down here are hotter than literally melting the iron. We boil water, average temperature in Death Valley, your human body, where it freezes, where we keep temperature at in your freezer. This is liquid oxygen. In other words, at this temperature, air turns to liquid. And then absolute zero is the temperature in which everything stops moving. All the particles would freeze. Okay, negative 273 degrees Celsius. We obviously don't do that stuff. Okay, so that's it for today. All we did is took notes. I didn't give you a quiz. Obviously, if we were in person, we'd give a little 10-question quiz here. But you got the notes for today. You can hand this in on Monday as a normal assignment. And then we'll finish the lesson talking about the other types of transfer today. After making it through the thing, you got your 24 down here. For number 25, you can pick one of the temperatures and write the temperature down for number 25. And I'll give you extra credit in science class for listening to the awesome video. Have a great day.